the Eddington approximation that
Absolutely.
I read in the book.
Okay, good. So I think what I've got in my lectures is inspired from Rybicki and Leitman. So as we go through them, you can stop me when we come to a point where there's something to clarify. Okay.
Sure.
Um, good. So one question I have for you: have you handed in your homeworks?
Not yet, Professor. So I have done up till 9 questions. So I have done in the rough one. So I have yet to do in like fair, like I have to write it properly for submission. So I have completed till 9. I was doing the 10th question. So it was taking some time. So I was stuck on that 10th question. And yeah, so yeah, so that is the status of my
Okay.
homework.
Okay. What about the others?
Yes, Professor. I have done until the I have done until the fifth question. Actually, I couldn't manage to couldn't manage the time to do. Yeah. So maybe I will do by the Thursday. I will finish it. Yeah.
Okay.
Mm.
Well, hopefully as soon as possible, and as soon as you're done, we can see if you are in adequate conditions to take the first exam. Okay, then we'll see, we'll evaluate that once everybody's handed in their homeworks.
So I can.
Right?
Hello. Uh, so I'm like. Huh?
Baja el micrófono.
El micrófono está saturado.
Tenés que bajar el micrófono un poquito. Creo que el volumen de tu input está, pero fuera de escala. Ya. No sé, ahora no se escucha nada.
Hola.
Ahora sí, un poquito más, un poquito más. Súbelo un poco más.
Hola, sí, hola.
Sí, ahí está
Hello,
mejor.
hello. Number 1, 2. Yes.
Good. That's.
Sorry, I don't know why that happens. I should check my audio before speaking. So I'm hello. I'm halfway through the homeworks, and yes, I'm also having issues with time, really. And but I was wondering, the level of the test will be more or less like the homework. So that's why the homework is how we should study.
Well, the exam is something I've invented, so it's not on the textbook, but it is similar to the last questions of the homework of the. Actually, it's inspired from the last two problems, I think, on the Eddington approximation. So it's yeah, but I mean, honestly, if I really believe that if you've done homework, it should be easy to do the exam in 3 hours. Nonetheless, if you're not feeling confident enough, we'll give you 2 weeks. That's okay. But I think it's not necessary. Okay. I think we can evaluate when I share the exam if anyone has got a serious problem with it, but I think it's pretty straightforward, especially since it is solved already in a couple of references I'll be citing in the exam. Okay, so don't worry too much about it. I think the most important for them, what you do have to worry right now is to close chapter 1 and hand in your homeworks, so we can get on with the rest of the topics. Okay.
Yes, thank you.
Professor,
Sorry, Nitya.
Professor, yeah, actually, me and Pratyush, we both want to share you something. So maybe Pratyush will explain everything to you.
Professor, actually, we would we would be comfortable if the test would be conducted in the week starting from 21st June, because we will be traveling to Santiago on 18th June. So we are more or less like occupied with preparing all the documents and all the items that are required for our stay in Santiago. So we are not uh, like fully able to focus on the subject right now, though we are managing whatever time we are getting in our hand to complete our work. But still, it would be, though we will submit our homework as soon as possible, but it's just that we want our exam to be in a in a stable environment, so that we can give our best in that exam. So if it would be better if this is a just a humble request from our side, that if that exam could be in the week starting from 21st June, because we will reach Santiago, like the scheduled arrival in Santiago is in the evening on 19th of June. So from then on we can be able to we will be stable at that time. That's our humble request, Professor.
Okay, well, first of all, that's great news. I'm very glad to hear that we'll be able to travel at last.
Yes, Professor.
And both of you have got visas then?
Yeah, so we our visas have been confirmed. Only thing that is required is the stamping, and we would have been in Santiago a month earlier if the pandemic in India would have not gone worse, or if I would have not contracted COVID myself. Uh, so we were not able to go again to our capital, which is New Delhi, for stamping. So we wrote the embassy that when we will be traveling, then only we will come a week earlier from our scheduled departure, and then they will take just one working day, and then they will stamp the passport. So more or less we will get the visa in 2 to 3 days. So it's just a matter of formalities, and they have accepted our request and they are okay with it. And we have informed them in advance as well that we will be coming in the week starting at on 14th of June, just before 3 4 5 days before our scheduled departure. So they have agreed to it. So yeah, so if everything goes according to the plan, we will be in Santiago in 19th June. Yeah.
Yes, so that's great news. Okay, I think you're probably worrying too much about the test, in the sense that, as I said, I mean, if you need more time, I can give more time. I'm okay to postpone the first test to June 21st. Handing the test on June 21st, if this is what would you prefer. However, we cannot postpone continuing with the lectures. I mean,
Yeah, sure.
what makes me uncomfortable is that we'll pass on to other topics. And so these introductory material about radiative transfer will be, well, we'll have passed beyond it, right? I mean, in the sense that we won't be discussing radiative transfer much anymore. We'll be focusing on microscopic processes rather than the transport of radiation itself. And so when the time comes to do the exam, we'll be talking about very different things. And that it was what makes me uncomfortable. But I do understand your position. I mean, it's fine. If you prefer to take on the exam, if you two prefer to take on the exam on June 21st, that's okay. Bearing in mind that by the time that you take the exam, we'll be talking about different things in the lectures, if that's all right. Okay.
I think it's fine.
Okay. So now maybe we should get started. Before I get on with the Eddington approximation, does anyone have a question or a comment about the Rosalind approximation? No?
Simon, when you were talking, I was checking my proof, and I found an error.
Okay.
But I have a link that could be useful. I'm gonna send it by the chat.
Okay. We'll look at it afterwards. Then I mean, we can all check the link later on. I'll get on with the lectures then, because we're already 20 minutes into the hour. Okay, so let me share screen.
Professor,
Yep.
Professor, I have a question regarding Rosalind approximation. So, as we have seen that if we combine both absorption as well as emission, sorry, if we combine both emission and as well as scattering, so we get a source function as S nu equal to 1 minus epsilon nu multiplied by J nu plus epsilon nu multiplied by B nu. But in Rosalind approximation, we assume that whatever intensity that we are getting is from just the Planck's function. So are we omitting emission? We are just considering scattering in Rosalind approximation. Like if, so, so my question is, when we are deriving Rosalind approximation, do we omitting the emission part and only considering the scattering part? That's my question.
Okay, I think you mean, let me go to the relevant bits.
Or maybe whatever perturbation that we are assuming is covered in the emission part, like it's more or less covering, because the emission is so low that is just a perturbation in the Planck's function.
Yeah, I'm searching for this expression you cited. What expression did you give for the source function, Tatiush? Can you?
So S nu equal to 1 minus epsilon nu in bracket multiplied by mean intensity J nu plus epsilon nu multiplied by Planck's function B nu. Yes, and when we are dealing with Rosalind approximation, we kind of only take the Planck's function. So I was.
Yes. Let me. I'm trying to remember where did this expression for the source function come from. I think it's something from the textbook.
Yes, it's from the textbook, Professor.
Yeah, maybe we should bring it up there, because I think, well, first of all, in the Eddington approximation, I mean, in the Rosalind approximation, the source function is not the Planck function. It's not exactly the Planck function. It's we approximate. Planck. Yeah, it's I mean, even though we say here for the thermal radiative process, the source function is the Planck function. Hold on, I'm trying to remember what was the where did this come from? Let me pull up the textbook so we can discuss it directly. So which equation was it, Tatiush? Do you remember?
It's equation 1.95.
Oh yeah, that's the one.
Pratyush, what you can do with that equation? If you can show it, please, Professor.
Yeah, yep. Just a second. I just want to refresh my memory. Where did this come from? He's pointing back to equation 1.28. Oh, it's because of the scattering contribution. Okay, yes, because it is doing isotropic scattering. Okay, but let me pull up equation
emission plus.
Ah, 1.28 is this. Okay, just here, well, that's a big deal. Okay, so that's the source function by definition. Okay, and the emission coefficient J nu, when we have, I don't know if it does scattering here, probably not.
Yeah, there we are not considering scattering, but here
Yeah.
we are considering scattering. Yeah, so it's
Okay, so I'm going
a
back
more
to
general case.
5 now. Okay, this was in 1.95, and I think this is, yes, this comes in because J nu includes the isotropic scattering. Yeah.
Yeah. So, but when we write Rosalind approximation, we just write I think Planck's function.
Yeah. So that's an interesting comment, Pratyush. Thanks.
I think what happens there in the equation number 95 is that so what you can do is to multiply the j on the two terms there, so you get j minus epsilon j. Then you can how do you say mix the term, join the two terms with the epsilon there.
I think that's what you mean.
And you get
That
yes.
That cancels out.
Yeah, so you can, so you get j plus, so you get j plus the sum with the epsilon, j plus.
That's what you mean, Felipe?
J plus epsilon minus b minus j. So you can say if j is rather than is like b, you can take these two. You can take these two out, and you get only j, which is p.
Okay. Yes, are you seeing my screen, Felipe?
Yes, that's why. So if j is equal to b or similar to b, if you can approximate j to b, then s is equal to j, which we say is equal to b.
So I think that's exactly it, Felipe. Thanks. And Pratyush, I think that I mean, you were intrigued by an aspect of the Rosalind approximation, which is indeed a bit kind of contradictory in the sense that we're saying that for thermal processes, the Planck function, for a thermal process, the source function is the Planck function. But however, this formula here, S nu, similar to J nu, is not really the Planck function. This Planck function is the mean intensity, right? The local mean intensity. That seems a bit contradictory. I think that to solve this contradiction, we have to remember that we're doing LDE. We're not really in thermal equilibrium, okay? So the source function, as defined in the textbook, includes the scattering part in the emission coefficient, okay? So we have to remember that S nu by definition is this, right? That's the source function, okay?
Professor, but when we are not considering scattering, I think then this definition holds true.
If there is no scattering, then alpha and epsilon is 0.
Yes. No. No, it's
It's
one.
one. Maybe it's one. Yes, I can't remember the definition of epsilon. But yeah, I think we agree, no? So the idea is that the source function is approximately the Planck function in the Rosseland approximation. Is that okay? Yeah.
Okay, so I think we are in a thermalized length. I think we are more or less ignoring the scattering, or maybe that scattering part is covered in the perturbation that we give to the source function. That could be the reasoning, I guess. I'm also getting confused, Professor. So maybe I will again think it again, and then I will ask you again. If it's
No,
okay,
I
then
think I think you're asking the right questions, Pratyush. It's okay. It's a bit puzzling because we are saying we're not in thermal equilibrium. We're close to it. We're in a situation which we call the local thermodynamic equilibrium.
yes.
And so the mean specific intensity is approximately the Planck function, but it's not exactly the Planck function. Okay, it's close to it.
Yeah.
Okay, it's not exactly the Planck function because of the gradient in temperature. Okay, that's the main reason. I think that we can.
Okay, yeah,
Okay.
carry on, Professor. Carry on.
Yeah. I mean, we can apply the Rosseland approximation to the radiative transfer of lines inside the stellar interior. I mean, when we're not using the scattering coefficient, when we're using the line emission only, is also applicable. Okay. So the small deviations to the, I mean, the small deviations from the Planck function are due to mainly to the temperature gradients. Yeah.
Yeah. Okay.
Okay, so I'll get on then. I'll continue with, well, one thing to remember here is this, right? Okay, so the Rosseland approximation is similar to diffusion. I mean, to the fixed laws for diffusion for the flux of a quantity being proportional to the gradient of this quantity. Okay, so that's something to remember. And the quantity here being the density of radiative energy. Okay. Now on with the Eddington approximation. So, okay, so this is a reminder that, yeah, we know this is, right. So equation 48 was a definition for the radiation intensity moments. In terms of the energy density, the radiation flux, and the pressure tensor, the radiation pressure tensor. Okay, it's also an alternative way to write these moments is the one given here in equation 63. This is what's most commonly used in stellar atmospheres. Okay, so well, these are there's the same moments cast in two different forms. If you pay attention here in equation 48, I'm integrating over solid angle. And of course, solid angle d omega is, I have to remember that d omega is sine theta d mu, sorry, d phi, which is the same as minus d cos theta d phi, and which is minus d mu d phi, okay, with the change of variables. And so we get on here, we write the moments in terms of mu directly. I think we had seen this before, okay? And so the first moment is directly the mean specific intensity. And then we have this radiation flux towards the z direction, which is h nu, and the second moment, which is related to the radiation pressure. So here we have like the connection between J nu and the energy density, or an H, and the flux in the vertical direction, and K. Okay, so these are the connections between the two. So the idea for the Ellington approximation is to say that instead of requiring that we are in local thermodynamic equilibrium, we will make a softer assumption. The idea is to approximate the specific intensity field as nearly isotropic. Okay, so it's again like a Taylor expansion, if you want, in the sense that it's not really a Taylor expansion, but it's like a multiple expansion where we have I nu, which would be like the monopole, like a term that's constant that's isotropic. And the first term in multiple expansion is the dipole, right? So this mu term here, this B times mu, is like a dipole. So we have usual spherical harmonics. So that would be here state S. So that would be L equals 0, okay? And that one here would be L equals 1, okay? So that structure here is I'm representing a spherical harmonic where we have this y 1, I think it's 1 theta and phi, which is proportional to cos theta, is what I'm trying to say. The connection with spherical harmonics is really not important. What I mean to say is that you must have seen this before, that when you expand a field or a function in 3 dimensions in terms of a complete basis, we normally use the spherical harmonics for the angular parts, okay? You know that the monopole is the leading term, then you have the correction, which is the dipole, then you have the quadrupole, okay? And so what the Ellington approximation does is to say that the specific intensity field is really almost isotropic, as would be as in the Planck function, but there is like a small correcting term which is dipolar, so it's a small correction, okay? And so we are approximating the specific intensity field in terms of a monopole and a dipole. It's better than to say that the specific intensity field is isotropic, it's completely opticalithic, or it's the Planck function. It's a bit softer, you realize that. So it's like a Taylor expansion in the sense that the anisotropy of the specific intensity field is small, is what we're trying to say, okay? Okay, so basically we are expecting that this term is small. The dipole term would be small compared to A. So we replace this expression, okay? So this is equation 64. We are writing I nu in terms of A and B, okay? So let me write it down here. So say I nu is A nu plus B nu times mu, okay? And we plug this into equation 63, which are the moments, okay? So for instance, then we'll have that J nu is the integral over d mu times A mu. Okay, so this would be the first of the moment equation, moment 0, okay? And so we integrate this and we realize, okay, so the first term, J nu, that would be the term, the first term is the only one that survived. This one is odd, so it integrates to 0. And then we do the same for H and K, okay? And so similarly, we get H nu equals B nu over 3, and K nu equals A nu divided by 3, okay? So here is something interesting. We see that J nu is A nu in the Eddington approximation. And we see that K nu, the second moment, or the pressure, the radiation pressure, is equal to the mean intensity modulo factor 1/3, okay? So this is equation 65. We have that K in the Eddington approximation, K nu is equal to 1/3 times J nu. And that is very similar to what happens for thermal radiation. So for the Planck function, we have that the radiation pressure is 1/3 the energy density, okay? So we could also realize that we had the same expression for the thermal radiation going back here, and we say, well, we have thermal radiation. If we have thermal radiation, I'll write it down here. For thermal radiation, A nu is the Planck function, okay, and B nu is 0 if we have purely thermal radiation, okay. And so we do the same exercise. We plug in A nu equals B nu, or A nu equals B nu. So this small b nu would be 0. We do the same calculation and we come up with, well, unsurprisingly, with K equals 1/3 J, okay? So when we have the Eddington approximation, we have something similar to the thermal radiation, but a bit more general, because we can allow some degree of anisotropy in the radiation field, okay? So the plane parallel radiative transfer equation, so this is so this is the plane parallel radiative transfer equation for isotropic scattering. Okay, so this is okay as long as we have isotropic scattering, which is the case for microscopic processes related to line radiative transfer. Okay, so this is equation 42, where we have agglomerated the scattering coefficient again with the absorption coefficient in a single coefficient, in a single alpha coefficient. Okay, and what's equation 46? All right, so this is the plane parallel approximation. We've been through that already. Okay, and we can rewrite equation 66 in terms of the optical depth coordinates. So we are writing this. Basically, we're saying that d tau, this is the change of variable we're doing to write down the same equation in terms of the optical depth directly. Okay, good. Now, if we average equation 67, which is the radiative transfer equation, so we are taking the 0 moment of equation 67, we get equation 68. So I think you must have seen this already in the textbook. I'm taking then the angular, so the first moment, this moment 0 actually, of equation 67. Maybe I write down equation 67, then it's mu times d. What was it? It's J nu plus S nu, I think. Let me remember. No, it's I nu plus S nu. Okay. I nu. And what we do here is then integrate this over d mu, all of this. Okay. And so obviously this is this is going to yield the mean specific intensity by definition. This one is just going to be still going to be the source function, since it's isotropic. Okay. And this part here is then okay. So that deserves a bit more explanation. So this part here is going to give us the integral over d mu times dd tau nu of mu I nu. So why is it that I can take out the gradient over the opacity outside? I mean, why is it that mu doesn't depend on tau?
Maybe it's isotropic.
I'm sorry, misheard.
Maybe it's isotropic. That's why, because it's independent of direction. Because mu is cos theta. Yes.
Well, we are allowing from some degree of anisotropy in I nu. Okay, that is the idea you were trying to expand upon here. Rather the idea is to say that I nu in the plane parallel approximation only depends on z. Well, no, that's not true. I nu depends on z and on direction. Okay, so that would be cos theta, the direction. Okay, but these are two independent variables. In this is like calculus in with multiple variables, when you have to define what are your independent variables. Okay, and here we're saying, well, I nu depends on two variables. They can depend on the direction and on position. Okay, but I can change z independently of mu. I can keep mu fixed and evaluate the specific intensity at different z. And likewise, I can also fix z and change mu. So in other words, z and mu are independent. Okay. So when I do the partial derivative over z, which is what's in the denominator here, then I can bring it in mu because it doesn't depend on z. Okay. They're independent. And likewise for the integral. So I pull out this partial derivative outside the integral, and what's left inside is the first moment, which is h. Okay. So we end up with equation 68. When I take the first moment of the radiative transfer equation, I get equation 68. And then I can do the same trick again. I take the first moment, and if I take the first moment, then like if let me put it in red here. Same. So it's essentially the same, but I'm now multiplied by an extra mu here. Okay. So in this case, I'll have an extra mu here. Okay. And this one is going to average out to 0 this time, because I'm integrating an odd function across 0. Okay. This one is going to give me h, because it's by definition of the radiation flux, and the left hand side will give me the second moment. When I'm taking the gradient over opacity outside the integral again. So we get to equation 69 here. Okay. Do you have any questions so far about this? Is it okay? Yeah. Okay. So then we replace the Eddington approximation here. Okay. And this was the Eddington approximation, equation 65. Okay. It is. Sometimes this is called also a closure relationship. Maybe you've heard of this concept when you solve a differential equation in a polynomial series. And so you say, you know, I'm expanding the solution to the Schrodinger equation in terms of polynomials. Each of the polynomial coefficients is a moment, because you say that the polynomials represent a basis of functions. Okay, and so you can actually reconsider the coefficients as moments of the I mean, like you have moment 1, moment 2, moment 3, the same actually. The coefficients are moments. Okay, and of course the solution in terms of a polynomial series is purely formal. I mean, it doesn't actually give you a solution unless you can truncate the infinite series. Okay, if you can truncate the infinite series with a closures relationship like this one, when we're connecting equation 65 connects moment 2 with moment 0. Okay, so this is a way to truncate the series. And well, it's also called a closure relationship. Okay, so we have equation 65, which is the Eddington approximation. Okay, we can plug it in here. So let me write down equation 65. So it was K nu equals 1/3 of J nu. Okay, and we plug it in here. Okay, so we say, well, equation 69 is going to give us, I'm plugging equation 69 into 68. Okay, so it's going to give me d tau times what was the idea? Oh, no, okay. I have to derivate equation 69 times okay. And so, and then I use the Eddington approximation for the left-hand side. And so that gives me 1/3 this second times J nu. And on the right-hand side, then we have dH nu over d tau. And then I use equation 68 to say that this is J nu and S nu. So we reach equation 70, where we have a single differential equation for J nu. Okay. And we replace then the expression for we replace the source function in terms of well, okay, here we use the same equation that you mentioned, Pratyush, at the beginning. Yes.
Yes. Yes.
Yeah, okay. And then we can rewrite equation 70 in terms of 71. Good. Oops, sorry. Yes, and so if we can obtain J nu, we can then recover I nu by integration of equation 67. Yes, because once we have determined, since the source function contains J nu, then we can, once we have J nu, then we have to integrate equation 67 to obtain I nu. So it's two steps. First, we solve for J. Then once we have J everywhere, we go back to the radiative transfer equation. So this is not the radiative transfer equation. This is a derived differential equation to obtain J. So once we've solved this somehow, if we can manage to solve this, then we go back to the radiative transfer equation, which is this one, okay, equation 67. And we now have correct expression for S nu. Okay, we're using the expression for S nu that Pratyush mentioned at the beginning. Up here, this is what we started with. S nu depends on J nu. Okay, so once we have J, we have S, and we can write down the we know how to solve this because then everything is under control. We have all the variables that we need to perform a numerical integration of this. Okay, so that's the Eddington approximation. And that's, well, you could say, well, we can solve this numerically. Yes, we can. But there is a problem, of course, which is what are the boundary conditions? Because when you define a radiative transfer equation problem, you need to know what the boundary conditions are. It's not so easy. Okay, so in this case, suppose that we have this. This is the situation. We have a uniform slab like this. Okay, and I'm saying, okay, we want to know what's J nu of Z here. So this is Z. Okay, so I have to specify J nu here and J nu there. Okay, in order to solve or some condition on the extremes at 0 and L. Okay. And so in order to find those boundary conditions, there is yet another approximation, which is a two-stream approximation, okay? So if you can understand all this, then you become really experts in radiative transfers, okay? This is as complicated as it gets, okay? All the rest is numerical, and actually I want Rafael, the teaching assistant, the TA, to explain to you how we solve the radiative transfer equation numerically using a package. Meanwhile, I mean, let me describe this. So we are saying the following: we're saying that the specific intensity field, we assume that the whole specific intensity is restricted to two directions only. Okay, so we have plus or minus 1 over square root 3. So what would be? I mean, let me see. Well, we're saying this cos theta equals to 1 over square root 3. How much is theta then?
54.73 degrees.
64?
54.73.
Yeah, it's probably, that's what it is. Is it pi thirds? I think so. More or less.
Yeah, 60 degrees. Pi by 3 is roughly 60 degrees.
Oh yeah, it's obviously. Yeah. So, but I think this is it, no?
Like what I got was 54.7, roughly 55. So it's very close to pi by 3. You can say that. Yeah.
I'm not sure about what I'm saying here. It's a question. What is theta if cos theta is 1 over square root 3? I'm not sure, but it doesn't really matter. Okay, maybe it's not. Maybe actually, the cosine of pi thirds might be. Is it? I'm not sure how much that is. Is it square root of 3 halves? Maybe that. I can't remember, but just wanted to fix ideas. It's you say, Patyush, that theta is
54.7 degrees.
Okay, I believe you. This is wrong then. Okay. We have this situation where how can I draw? I mean, like this is Z here. This is theta. And this is 54.7 degrees, okay? So what does it mean that I nu is only travels in this direction? How can we write this down? Well, we have here an expression for it, equation 72. Now pay attention to this. We have, I'm writing the specific intensity in terms of two directions only. I used the Dirac delta function for mu, meaning that I nu is 0 except when mu is equal to 1 over square root 3, where it's infinite. Okay. And I do the same for the negative direction. Okay. So how do you picture this in terms of in a three-dimensional structure? What would those beams look like?
Professor,
Yes.
the two-stream approximation always use mu equal 1/3 that number. Can the two-stream in approximation can be used with another number?
It can be used with another number, but you'll see that this number is convenient shortly.
Okay.
Okay.
Thank you.
But how do you picture this beam? What does the beam look like?
Like a cone?
Exactly. So it's like a cone. It's like something like this. So this is the radiation field that we are looking at, okay? Like two cones, okay? We're saying, let's imagine that the specific intensity is given by this expansion in terms of delta functions. When you evaluate the specific intensity moment, and this is easy to do because you know the integral of the delta function is 1, okay? You get this expression, equation 73, okay? And we see that in the two-stream approximation, the Eddington approximation holds. So the Eddington approximation was for a mildly non-isotropic field. So we say the specific intensity field is a monopole along with a small dipole, okay? But here we're looking at something quite different. We're saying that we have a cone. It's not a monopole, it's a cone, okay? It's completely anisotropic. Yet it fulfills the Eddington approximation because when we evaluate J and K using this expression for I, we recover these expressions then for the moments, and it turns out that indeed K nu is 1/3 of J nu. So this means that equation 67 will, I mean, so yes, yeah. Oh, Nidya, go ahead, just interrupt me.
Okay, yeah, thank you, Professor.
Oh, we have to leave because of the lecture.
Yes, I have lecture actually.
Okay, Dan, we're almost there. I took too long. Sorry. Okay, well, to make a long story short, I'll finish this on next Thursday, but the two-stream approximation yields the Eddington approximation. It's a specific intensity field, so it satisfies the radiative transfer equation, okay? Well, we can connect, you can use this trick to write the boundary conditions, because here we have an expression for J nu directly. We have J nu in terms of I plus and I minus, and we say that in the border, I minus is 0, and in the other side, I plus is 0. There's no radiation coming from infinity. I'll repeat this on Thursday, okay? All right, that's it for today. Maybe I should go faster next time. Sorry. Ciao.